3.3. Today we travel to infinity and beyond. We're going to be looking at limits involving infinity. With that, we're going to be looking at vertical asymptotes and horizontal asymptotes and slant asymptotes. Okay, remember vertical asymptote would be vertically, horizontal would be this way. All right, so let's dive right in. All right, here's the definition of a vertical asymptote. If you take the limit as x approaches a number, either from the right or from the left, if you get positive or negative infinity, that means that it's shooting up so fast that there's a vertical asymptote there, or shooting down so fast that there's a vertical asymptote. Okay, so we would be able to evaluate these quickly without a calculator because we can transform our functions. We know that that is just a transformation of the function 1 over x. So it's 1 over x flipped over. That's what makes the negative. The 2, remember, stretches it a little bit. And the x plus 3 moves it to the left. So instead of having a vertical asymptote at 0, it's going to have a vertical asymptote at negative 3. Okay, and then it would be flipped opposite what we would normally see. And it would look something like this. So if we evaluate the limit as x approaches negative 3 from the left side, we would be going towards infinity. Okay, this part B, it's going from the right. So as we get closer and closer to negative 3 from the right, we get negative infinity. Okay, as x approaches negative 3, we're coming from both directions. They are not approaching the same number, so the limit does not exist. Remember, the left-hand limit doesn't equal the right-hand limit. Okay, those ones, pretty simple. We maybe don't recognize what 4 minus x over x minus 2 looks like. However, we do know that we could break it down using our properties of limits to this, okay, minus limit as x approaches 2, x over x minus 2. Okay, let's say your calculator is not with you right now. The limit of a constant is always just that constant value. The limit of x, plug in that number. Okay, now this part. Think about what this is going to look like. This function has a vertical asymptote at x equals 2. So we're not going to be able to plug in 2. Okay, from one side of 2, it's going to be positive. From the other side of 2, it's going to be negative. So that doesn't exist. So then the whole limit does not exist. All right, so we have a couple different ways of looking at limits of at infinity. So we could have a function like x squared, where if we approach infinity, the numbers are just going to get infinitely larger, or infinitely larger going the other way. Other functions, they might level out. Okay, so we could have something that looks like this, and it kind of levels out. All right, so let's look at these specific things. If our functions increase without bound, like x squared, the limit as x approaches infinity is simply going to be infinity, or negative infinity. As we approach negative infinity, it continues to go upward, so it is infinity. The graph can decrease without bound. Okay, it could look like this. If that were the case, both of these would be negative infinity because the graph is continuously going down forever. The graph can oscillate between two fixed values. So sine of x looks like this. As we go towards infinity, this isn't stopping at a specific value. Instead, it's going back and forth between -1 and 1. So these do not exist because it's not limited to a specific number. Okay, it's within the range of -1 to 1. Or the graph could taper off towards a specific finite y value. Think about 1 over x. Okay, that looks something like this. So it's going to taper off at the end towards 0, or a specific number, some constant value. All right, the last case is what we see as a horizontal asymptote. That is the definition of the horizontal asymptote. Okay. Horizontal asymptotes are not discontinuities. It's not a vertical asymptote where it's going to jump from one side to the other. It's just kind of tapering off to a specific finite value. We're going to look at different cases, and we reviewed some of this in pre-calc. Okay, if the degree of the denominator is greater than the degree of the numerator, then the bottom is going to grow so much faster than the top that each time the limit as you approach infinity is just going to go towards 0. Okay, so think about a small number over a big number. That's going to be close to 0. The further and further you go, the higher numbers you put in. It doesn't matter if you're going to negative infinity. That's going to be the same case. This highest power is 5. This one's 2. 5 grows, x to the 5th grows so much faster than x squared. Okay, another case, the degree of the numerator and denominator could be exactly the same. If that's the case, then they're growing at the same rate. So for this first example, it's like you have $3 million over $5 million. And for that, you just take the ratios of the lead coefficients. So this one is going to taper off around 3/5. Okay, when you put in negative infinity, well, you have 3 to the negative, okay, that's going to be a negative number, -3. And then 5 to the negative something really big. That's going to be -5. This one ends up tapering off to 3/5. So that means for this function, you have a horizontal asymptote at y equals 3/5. All right, our last case is when the degree of the numerator is greater than the degree of the denominator. Okay, so in this case, the numbers on the top are growing bigger than the numbers on the bottom. What happens is, usually if it's 1 degree difference, there's going to be a slant asymptote. So it's going to either continue upwards without bound or downwards without bound. Okay, and you can tell by what sign you put in. If we put in a positive infinity here, the top will grow larger faster, so we're going to get a positive infinity as our limit. If we put in a negative infinity, this one is going to go towards positive infinity. If we put it in here, negative numbers cubed, that's going to give us another negative number. So we have a positive over a negative. That'll give us negative infinity. Okay, all we had to do is plug in big numbers. So we're going to look at the specific case of slant asymptotes very soon. Probably, we might as well save that for the next video. Okay, so what I would like you to do is just write the answers to this example. Okay, the one on the next page. Write the answers to this in your WISC. All right, have a great day.